Hello everyone, my name is Manira Mahmoudi and I am an assistant professor of College of Agriculture and Natural Resources at Michigan State University. Um, I have the privilege to be the session chair today for this particular session that I'm handling. So we have 6 presenters and I would like to start with the first presenter and read the very short bio for this student. Chayan Siriaco is a PhD student in civil and environmental engineering, specializing in transportation engineering at the University of Alberta, Canada, and a member of the Resilient and Sustainable Mobility and Evacuation Group, RESUME Group. With the RESUME Group, Tayan is researching evacuation, human behavior in disasters, and resilience hubs. So, stage is yours. Please mute. I will ask everyone to mute their speaker, and let's get started with the 16 to 17 minutes presentation. Thank you.
Can you see my screen?
No, yes.
Okay, thank you. So hi everyone, I'm Tayani, and today I'm going to present my research on measuring resilience hub coverage across transportation modes, a case study of Edmonton, Canada. The outlines of this presentation is a brief introduction, the methodology used, the results, and I provide some key takeaways. So the rapid urban growth and the increased hazards have challenged urban systems and their functions in many cities. And this has led to significant human and economic losses that can rise, are going to be expected with a changing climate. So these communities need to increase their preparedness, response, and recovery capacity in climate and non-climate change emergencies. So in this case, these communities require new ideas and tools to ensure that the residents both survive and thrive. And what we need to ensure? We need to ensure that they are going to evacuate safely from risk areas, finding and operating sufficient and livable shelters, connecting resources with survivors, and assisting people in everyday basis. And a new idea that come up to address this is to create resilience hubs. Resilience hubs are community service physical spaces, the building and the surrounding area that is created to support residents, coordinate communications and resource and communication service and provide resource distribution before, during, or after disaster. These facilities work year-round in 3 different modes. In everyday and normal mode in the majority of the year. When the disruption happens, they shift to the disruption mode. After the disaster, they go to the recover mode until the community is recovered and they go back to the everyday or normal condition. And the case study that we are evaluating here is Edmonton. Edmonton is located in Alberta, Canada. And a little bit overview of how is the Edmonton area distributed. We have this map showing the land use. The red areas are residential areas. Greens are forest or farmlands, and the orange are the industrial areas. This map is important to understand the coverage analysis that we are going to have in the later results. So the study objective is to identify existing buildings that can be retrofitted to serve as resilience hubs. We decided to select community league halls, public libraries, and recreation centers based on previous studies that indicated that people are very satisfied to have these buildings retrofitted into resilience hubs in the Edmonton area. And then we analyzed the 3 scenarios. The first one, all community leagues serving as a resilience hub. The second scenario is all public libraries serving as a community, as a resilience hub. And the scenario 3 is all recreation centers serving as a resilience hub. For those of you that may not know what's a community league, they are neighbor-based nonprofit organizations that meet community needs through communities defined programs and service, and they often have their own facility, including a community hall or sports centers facility. And to be able to conduct this research, we got some data from open source portals. For example, the neighborhood boundaries and dissemination areas came from the City of Edmonton Open Data Portal. The road network, land use were from the GeoFabric shapefiles. And we got the GTFS, that is the public transit schedule from open mobility data, and the demographic information from Canadian census data. The methodology was to first obtain the data, and after that, we prepared this data to be added to QGIS and to R5R. In R5R, we obtained the isochrones for 15 minutes and 30 minutes travel time for 4 different modes: walk, bicycle, public transit, and car. For public transit, we consider 2 different scenarios: the peak time scenario and the off-peak time scenario. After that, we joined the demographic data to the QGIS. Then we added the isochrones and intersect these isochrones with the dissemination areas and demographic data. We then calculate the coverage of population, the residential area coverage, and the percentage of neighborhoods that are covered by these resilience hubs. So we also had to assume some values for the R5R code, and the walk speed and bike speed used was the default value of 3.6 kilometers per hour for walk speed and 12 kilometers per hour for bike speed. The maximum number of public transport riders allowed was 3, and the maximum trip duration for these transit rides was 30 minutes. And the time window used, that is the period of time considered to create multiple travel time matrices, depart in each minute, and to return the median travel time was 120 minutes. For the bicycle, we had a maximum comfort level of traffic for cyclists that was tolerable for the mainstream adult population. This includes the streets where cyclists have dedicated lanes and only have to interact with traffic at formal crossings. The departure time for peak was 8 a.m. on a Wednesday day, and the off-peak was 12 p.m. on a Wednesday day. The day were chosen because it was not a holiday and was a normal day. And the time intervals was 15 and 30 minutes, and the public transit considered the best scenario of a combination of walk and transit. So the results that we got was that in 50 minutes, these are the areas covered by community leagues. The community leagues had the best scenario among all 3 scenarios, but we can also see that even then being the best scenario, many of the residential areas, that is the gray area, are not being covered. And bicycle had a better coverage than walk, that is the yellow on the top left, and the public transit scenarios, peak and off-peak, in the bottom. The same was observed for libraries, where bicycle had the best scenario, but they have a lower coverage than community leagues. And also recreation centers, they also have the bicycles as the best scenario for them. And the recreation centers had the lowest coverage. In all scenarios, we are not showing here the driving, because by driving, the residents could reach almost the entire city in 50 minutes. We then analyzed it in 30 minutes, and we observed that the community leagues, they had a better coverage in 30 minutes than 50 minutes, but we still have some residential areas in the northwest and in the southern Edmonton that were not covered. Then we analyzed the libraries, and we saw that a little bit of the residential areas in the south that were not covered by community leagues now are covered by public libraries, but we still have residential areas not covered by libraries or community leagues in 30 minutes. The recreation centers again had the worst scenario. And in all these 30-minute scenario coverage, the bicycle had again the best scenario. So a summary of these parameters that we analyzed, we could see that community leagues had almost half of the population be covered in 50 minutes by walking or public transit during peak times. And bicycle could cover almost 90% of the population. But libraries and recreation centers, the coverage of walking in 50 minutes was very low. It was about 8% for libraries and 5% for recreation centers. And this scenario was also not good for public transit, that we had 10% and 5.5% of the population be covered. And by bicycle, a little bit more than half of the population could be covered by libraries and recreation centers in 50 minutes. And as you can see, in 50 minutes or 30 minutes, almost 100% of the residents could be covered by a resilience hub in any of these scenarios. But when shifted to the 30-minute scenario, we could see that community leagues can cover more than 80% of the population by walking. And libraries and recreation centers increased the coverage for walking for 34 and 29, but these values are still lower than the 50-minute scenario walking for community leagues. And so the key takeaways that we got from these is that in nearly all residential areas and population would be covered by driving within 50 minutes, regardless of the scenario. No scenarios with non-driving modes could cover the entire residential area, especially in the northwest and southern areas. I highlight here that the southern area is a new area in Edmonton that is still in development. Most of the coverage deserts were observed in industrial areas and green space. Bicycling coverage level was better than public transit coverage in all scenarios. Community leagues can cover a large area in 15 minutes and in 30 minutes, and new scenarios combining these existing buildings need to be tested to obtain the best scenario for demand and supply. Another point that we got is the limitations. The calculation of the population is based on the proportion of the area covered by the isochrones. The isochrones results are based on specific days and times of the day. So in a different day, it may change the public transit coverage. That's why we assumed a normal day that was not a holiday with normal traffic. The assumption made for bicycling may not be ideal for all ages or people with mobility constraints, and the study does not evaluate the economic feasibility of retrofitting the existing facilities identified in this study. Another problem that we could get is the capacity. Although community leagues, they have the best coverage scenario, they have the lowest average area. And recreation centers, they had the worst coverage scenario, but they have the highest average area in their buildings. So next step for this study is to combine these facilities and consider the scenario where the capacity is considered, and then we can optimize the location of these resilience hubs in these different buildings. I'd like to thank my co-authors and funders, Professor Stephen Wong and Professor Emily Grisset, and the funders, the City of Edmonton, Alberta Eco Trust, MyTax, and Canada NRC. If you have any questions, I'm happy to answer. And you have here some QR codes for the papers about resilience hubs.
Thank you, Tayani. So let's wait for any question or from the audience. Ward appreciated the presentation. Alex also appreciated the presentation. We still have 6 minutes for Tayan to, if not, let's move to this. Yeah, any
Yeah, it's not a question, but I'm just interested, like if the demographic analysis can be done with this data, like which demographic group has better access to this resiliency hubs, that would be good, I guess.
Thank you. It's a good point. We started to look at it. We saw the areas where we have more, for example, low income or visible minorities and other underserved populations in Edmonton. And this is also going to be part of the next step when you're going to optimize the locations to ensure that when we choose the resilience hubs, they're going to cover the communities that most need, because we understand that the city cannot have 100 of resilience hubs in the city. They need to start from some point, and the start point has to be the communities that need the most.
Yeah. Thank you.
You're welcome.
I have maybe a quick question. Is in the metrics, was there any difference with the cycling winter versus the fall? Was that something that was considered? I mean, Edmonton is pretty challenging winters for sure.
We do not consider the weather in this study. We just consider the normal scenario because it was the first step of the scenario. And now we are adding constraints to this to obtain the optimized locations. And for sure, weather is one of them, because during the winter is a terrible winter. Is some days is a lot of snow and very cold. But Edmonton has many bike lanes, and they are increasing the bike lanes as well. So I think people here, they are pretty much active even during the winter. But we are going to add some of these constraints in the next step of this study. Thank you for the question.
awesome. So if there is no any further question, we can move to the second presenter. Mr. Eric Peterson is the transportation modeling lead for Mott McDonald's in Toronto. He has more than 20 years experience in transportation field, and his recent work has focused on forecasting the medium and long-term impacts of COVID on transportation systems, coping with severe uncertainty in travel forecasting, and addressing equity directly in travel modeling. So the stage is yours, Eric.
All right, thanks so much. I'm going to see if this works. Okay, so I can't actually see anymore. Can you see this the slide or no?
Yes.
Okay. So this is work that I've been doing a lot with Dr. Matthias Sweet from TMU. We've been working on and off with car sharing probably since 2012 or so, and Dr. Scott from McMaster has been involved more recently with some of the more recent data collections. I apologize in advance. This is a kind of a data dump presentation, and I won't go through everything. I'm going to hit some highlights, and the slide should be available kind of on the Google Docs thing. And if not, reach out to me and I can send the full presentation, because I just, it's too much data. But anyway, car sharing is an interesting phenomenon. It's something that's become much, much more common in North America anyway, since kind of the mid 90s. And it really took off in the late 90s through the early 2000s, 2010s. And you know, it's considered one of many travel demand measures, demand management measures, because ideally people will get the car sharing and then they will be so enamored of it that they shed a car. Like they go from say 2 household vehicles down to 1 or 1 to 0. Now, what is a little unclear, and this is not actually the point of this research, is no question, households that shed a car travel, make less vehicle VMT or VKT. But on the flip side, you have households that were zero car households, and now they have the ability to kind of drive. And so it's unclear the offset. And so that actually is interesting from a modeling perspective. Like, well, now you've got these zero car households out of your car ownership model, and you have to then say, suddenly they actually have access to the drive modes, which often in mode choice modeling and these forecasting systems, they don't. So I
Sorry,
am on
Eric,
another.
sorry to interrupt
Sure.
you. Could you share your slide in a slideshow mode?
Okay, I'm gonna try. So how do I do that in Zoom?
Just click on just the presentation file. Go down, please. Yeah, and so
like custom slideshow or present in Teams? Or?
Yeah, because probably the one that you see close to the Zoom sign in the down part of the presentation file. So do you see that? Yes. Yeah. The one at the right. So if you go down, yeah, a little bit down. Yes. Yes.
Down
yes.
here?
The other one. Go. Yeah.
This way?
Yeah. Yes. Click on this. Doesn't work.
Or also you can just click from beginning, I guess, that on the top left corner. Yeah, that should work, I guess. If you double click it, it should start from the beginning in a slideshow mode.
So the slides are not advancing?
Probably.
Actually, like we can see the whole screen here.
Oh,
but
that's weird.
Yeah, including your comments. If you double click on that small icon in the bottom corner, like Monira was showing you, if you double click it, then it should just make the whole
a little bit down, and again the other one close to yes.
Yeah, just double click it, I guess.
Okay, still doesn't work.
I guess I have your slides downloaded. I can share it from here if you want. I can.
Well, if you could, I'm sorry, I don't understand
No, it's
why
okay.
it's not working.
Let me try like opening your slide, whether I can open it from here.
Let's see here.
Yeah, I have your slide here, so.
Okay.
Yeah, let me just share my screen and then change the slides from here.
Sure.
So can you see the screen now?
We don't see.
Let me check. Let me try again.
Tayan, have you stopped sharing the screen, Tayan?
I think Eric needs to stop sharing his screen, then I can start sharing from here.
Okay, I did that on behalf of her.
Yeah, let me try again. So,
I don't think my screen is being shared.
I stopped it. I
Okay.
stopped it a few seconds ago.
All
Okay,
right, I see
thank
it.
you.
Okay, let's just jump to slide 5.
So you can see the screen right now, right?
Yeah.
Yes.
So this one?
Yeah. So I'm just going to jump in. And so one of the interesting things about car sharing is that it's either kind of a one-way system where you can pick up the car and drive it anywhere and drop it off inside a zone. And in Toronto, the zone is kind of like this pinkish area. Or you can do what's called two-way car sharing, where you rent the car and then you have to bring it back to the exact same station. And there's, again, a lot of research in this between which is more effective, which is kind of generating more reduction in cars. And generally, the flexible one seems to be more useful. Commute Auto is the major car share company in Toronto right now, and it is a hybrid where it actually does both, which is kind of interesting. Next slide. So when we were looking into the thing, one of the things is car sharing is very dynamic, and even before the pandemic, in the sense that uh, car to go was a very big car sharing system, and it ended up vanishing from first from Toronto and then in all of North America. They just pulled out of the market completely, and then new entrants came in. And so we said, really, you end up having to do a lot of scenario planning if you're going to be forecasting the impact of car sharing, which is what is an interest to me. And so we thought, well, you could double or triple the number of the car lots. You could look at where the flex zone expands dramatically. You could say, well, what happens if AVs come along, like or Waymos or something. And if you flick to the next slide, what happened is we were trying to think of all kinds of things, but we did not think about a pandemic. That just wasn't on our radar, as it was not for most people. So the next slide talks a little bit about what the data sources is, and we are very fortunate that we have 4 waves of a survey in the Greater Toronto and Hamilton area. 2 are from 2016 and 2018 before the pandemic. There was one 2021, kind of the tail end of the pandemic where most restrictions were lifted, but there still was a major reduction in travel. And then there's a more recent one, 2023 post-pandemic. And so we thought, well, this is a perfect opportunity to kind of look at the impact of the pandemic on car sharing. Okay, next slide. This just tells the region. I'm going to go over it super quickly, but Toronto is the pink kind of at the bottom center there. That's the big city. And then the colored area is what we call the GTHA, which is several, essentially very large counties around Toronto. Okay, so the next slide talks about the actual results. And again, I can't go through all of them, but what if you look at the yes number, that's who said they had a car sharing membership. So you get a card that allows you to use a car share system. So it was 7% in 2018, it was 9% in 2021. We had assumed this would drop like a rock because people really weren't traveling very much, particularly in 2020, but even in 2021. And then you look at 2023 and it's exploded to 22%. So it's over doubled. And even in the weighted results, it's very similar. It's even maybe more interesting. That goes from 8 to 13% and then 19% in 2023. So the next slide, we said, well, okay, maybe the car membership is a bit of a lagging thing. You just kind of keep it in your wallet. You're not really using it. And this looks a little bit at the geographic variation in the region. As one might expect, Toronto, being the most urban and having the most car share sites, is by far has the highest density, essentially, of car share membership. But Peel region, which is our next door, also quite an urbanized area, is pretty high, but it's lower in other places. Okay, sorry. The next slide talks about the usage. And so one of the questions, well, how often do you use a car share car? And again, we assumed this would drop dramatically in 2021, but it did not. I mean, it dropped a little bit, but uh, but really not much. And then so this 3 to 4 days category goes from say 1 to 2%, actually increased a tiny bit. But in 2023, it goes up to 8%. So even though it's not a huge mode share, it's still pretty substantial when we almost a quadrupling of people that are using car share 3 to 4 days a week, which is quite a bit. Now, this doesn't mean they're commuting with it. It could be any kind of a trip. It could be just going to the grocery store. But nonetheless, it's a pretty high usage of the car sharing. And again, we had anticipated this would drop a lot more. So we've been speculating, well, what does this mean? And why would it not have dropped? I think the most likely reason for the car share usage not to have declined is one, Toronto and the region have a pretty high number of what were called essential workers who really did need to travel. And in a lot of ways, the car sharing was like maybe the second best solution, right? If you were trying to avoid transit or other kinds of situations where you'd be exposed, you could be in the car share, even though it was still kind of shared. And as we found out more about the vapor transmission, some people got very worried. But it still was maybe if you had to travel, it might still be better than going in transit. Okay, so the next slide just talks a little bit about the demographics. So we were looking at the car share membership by income. And what is very interesting, not completely surprising, car share is really not seen as like a way to supplement low income households with 0 or 1 cars. It's just not really what happens. Instead, it's a more of a middle or indeed an upper middle class phenomenon. So particularly when we look at 2023, kind of like the post-pandemic explosion, we are up to 50% of people in the 175 or above household income have car share membership. And yet it's 9% for kind of very low income. So it can be very useful, and it can be particularly useful kind of convincing middle and upper middle class households to shed a car, but it's not really going to be part of an equity strategy per se, unless there were programs and outreach, to specifically target lower income households. Okay, next slide. I'm going to skip over this one. Next slide. So we also happen to ask race and ethnicity on these surveys, and what we found was that so we already saw that it doesn't really track that well against income, or at least low income. But what is interesting is that Black households and Asian households are slightly more likely to be car share membership and using the car share than white households. Now, probably this has to be crossed by geography, because one of the things we do know is that Toronto and Peel in particular have pretty high proportions of visible minorities, whereas the outer parts of the region do not. They're more more white, and so we'll have to kind of repeat this, doing a cross-sectional analysis of kind of combining the race, ethnicity, and the geography, but we didn't get there yet. That's probably what's explaining this. Okay, next slide. Basically the same thing we again see with the usage, and again, particularly the 2023 post-pandemic usage, Black households are twice as likely as whites on average to be using car share kind of in this moderate level of 1 to 4 days a week. And actually, when we look at the high usage, 5 to 7 days a week, it's 5% versus 1%. So again, it's interesting. I think we have to tease this out and look a lot more at the geography. Next slide. Okay, so I've already talked a little bit about it. We expected to see a decline, not just in the membership, but the usage. Didn't see that during the pandemic. At the most, you can say, well, probably the pandemic suppressed what was a pretty high growth that then exploded post-pandemic. As car sharing kind of becomes more attractive as the pandemic experience has faded. And the last slide, I'm just going to talk a little bit about the next steps. So we need to really dig into the 2016. Most of the tables that are in the PowerPoint are 2018, 2021, and 2023. So we want to look more at 2016. Really want to look at the zero auto household activity, what's going on. That's probably the most important from kind of a environmental TDM perspective to see what's going on with these households. Really look at the weighting of the data. I'm not 100% satisfied with the weights for sort of mixed race and other visible minority households. And then just really looking at the interaction of income, race, ethnicity, and in particular geography and density to see if we can get some kind of clearer findings. And then, yeah, we talk a little bit about how we'll probably pool the data going forward. So that's it. Thanks again for the technical assistance. Sorry about that.
No worries. Thank you so much, Eric. So we are open to the questions. Any question?
If audience doesn't have any question, I have one. Like, I have two actually. Is this data publicly available?
The short answer is no, but it would be possible to reach out to the professors at TMU and McMaster, and if so, the short answer is no, it's not. But I think there'll be ways to participate and support the research. I mean, I
Okay.
can't speak for them; it's their data, really. But it's happy to put you in touch with them.
Okay. And the second question is like you showed like how the car share usage and membership like varied with different demographic groups. So does the questionnaire had anything related to the destination people are using for like using this membership?
Yeah, no, it's a great question. So the short answer there is no. I think there's might be a Metrolink survey where they still don't the destination they know a little bit more, and it's also a question of trip purpose. So if you can kind of get trip purpose and say, oh, this was a car share for work versus school versus shopping, it's probably more useful. This wasn't really supposed to be a travel diary. This actually, interesting enough, was a survey about autonomous vehicles and attitudes toward them, and it just happens that Dr. Sweet and I were interested in car sharing. It's like, let's take the opportunity to add that in. So the focus of the whole of these surveys was really like, are you interested in AVs? Would you buy an AV? Would you take an AV? And there's only a little bit of questions about the car sharing. So it's actually a super interesting study, but this is kind of what we've extracted just out of personal interest. There have been a handful of household surveys that have completed recently where I think they asked about car sharing, but I don't know if they added in like the vehicle type, like, oh, this happened to be the vehicle that was a car share vehicle. That's really what has to happen to answer the question really. But so unfortunately, no.
Okay, thank you.
All right. Any other question? If not, the next speaker is Edward Monroe. Is a master student in transportation engineering at the University of Alberta, whose research focuses on active transportation accessibility and universal design. He is registered and engineering training in Alberta and has prior professional experience in transportation, municipal utilities, and resource extraction. Okay. Is Edward here?
Oh,
Okay,
yes.
good.
Hi, I'm here. Thank you for the introduction. I'm setting up the presentation. Okay. All right, am I good to go?
Yes.
All right, perfect. Hi, everyone. My name is Edward. Today I'll be talking about my literature review on shared use paths entitled A Review of Existing Designs and User Experiences via Lenses of Universal Design and Sustainability. So to begin, what exactly is a shared use path? Well, this image provides a pretty good example. So it's essentially a pathway, but it's allowed to be used by multiple different modes. So we have a runner on the left, we have two people on bicycles, but as you can see, it allows the different modes together on the same path. A little bit of background. So these pieces of infrastructure are really growing in popularity. They're often seen as low-cost methods to provide cycling access in a city. They're relatively space efficient. You know, you don't have to have separate bike lanes and sidewalks. You can just build one of these instead. And it encourages active transportation methods. So that's your walking, cycling, skateboarding, inline skating, etc. However, combining these different modes can often pose design challenges, right? So you're dealing with a wide range of uses, including cyclists, pedestrians, roller skaters, skateboarders. And so there's a lot of questions around safely. How do you properly design these? And that's really what started off this investigation. So how exactly are shared use paths designed? How do people typically use shared use paths? And then looking from a different perspective, how are sustainability and universal design principles part of shared use path design? So we answer this through a systematic literature review. We identified all the literature available on TRID and Scopus. Much to our surprise, there wasn't very much literature out there. As you can see, as we went through the screening process, we only ended up with a handful of papers. What are the key findings that we found? Well, typically, shared use paths are designed to be about 3 meters wide or 10 feet wide. So in the literature, this is typically where most users are comfortable, where there's adequate passing room. It's generally a good balance between that capacity and comfort. Another big finding from the design perspective has to do with center lines. So if many of you have taken shared use paths in your own communities, sometimes you'll see paths with center lines, sometimes you'll see paths without them. The literature actually finds that center lines are not a gimmick. It avoids a lot of wrong way travel. It has a statistical increase in overall capacity. And so these are really interesting design finding there. And another finding is, and probably the most important finding, is that shared use paths really aren't appropriate in all use cases. They serve a middle ground where you need to provide access to both pedestrians and cyclists, but where you don't have very high user volumes. And so if you're in a situation where you have high user volumes or high conflicts between users, shared use paths are not the best option. Specifically from the user behavior side, there's plenty of different types of users. Most of the literature focuses on cyclists and pedestrians because they are the most common users of this infrastructure. Specific to cyclists, they actually would prefer bike lanes over shared use paths, which generally makes sense, but they will also choose a shared use path over the road. Another thing with cyclists is they have a tendency to not use their bells. So this image here is a really good example of a local government trying to get cyclists to use their bells more often. On some paths, the non-usage of bells can get as high as 82%, which is a really big safety concern and is something that should be taken into consideration when designing these paths. Looking at pedestrians, they use shared use paths very differently. They're much slower than cyclists. Key findings from their behavior is if you have a large group of pedestrians who use shared use paths, they really like to block paths. They like to spread across the entire width of a path, and this can cause traffic flow issues on shared use paths, something to keep in mind. They're also sensitive to very high speed bicyclists, so something to keep in mind if you have a lot of cyclists in your community. And a really interesting finding was actually that runners cause a significant amount of conflicts on shared use paths. Perhaps something to do with listening to music, but it's very difficult to know why that happens, but it is an important finding. Some other highlights, wheelchair users, they're the least comfortable on shared use paths. And interestingly enough, if you want to look at incident rates, the highest incident rate on a shared use path actually comes from inline skaters, not bicycles. So that was another really interesting finding. So getting to more the meat and potatoes of our research, we wanted to see how universal design can be incorporated into shared use paths. So there are 7 main universal design principles. The first one is equitable use. So paths should have the ability to serve all users equitably, regardless of who they are. So this image provides a really great example of that, where you have someone using a mobility device and you have children there. Really great example. Flexibility in use. So shared use paths need to be able to support multiple activities and abilities. So this sign is a really interesting example where many shared use paths actually permit horses on the shared use path. So that's a really great example of applying flexibility and use to a shared use path. The third principle is simple and intuitive use. So you should be able to use a shared use path intuitively. It should be known regardless of language, age, cognitive ability. It should be very clear how to use a shared use path. And this image here from New York City is a really great example where there's clear line of demarcation. There's pictograms on the ground indicating who's allowed to use the pathway. Very clear, very simple and intuitive to use that path right there. Number 4 is perceptible information. So this is a little more complex, but the idea is information about the path should be communicated through more than just visual cues. It should include tactile or auditory cues if possible. Really, you want to engage as many different ways of perceiving information as possible. And so this image here is a really great example of using tactile features to convey information to path users, right? So people with visual impairments are able to use their walker, their stick, and they can feel where the path is taking them and if there's any hazards that they need to be aware of. This is a really great example of making shared use paths with perceptible information. Number 5 is tolerance for error. So for people using shared use paths, it should be very forgiving. It should minimize risk from unintended actions. So for example, that image for it is bridge railings, right? So if someone trips on the shared use path, they're not going to fly off the bridge and into traffic or into a river. So it's a really great example of tolerance for error there. Number 6 is low physical effort. So the design should be accessible to users with limited strength or limited mobility. Now, there's not too much you can do about this if you have slopes in your city, but you can make the experience easier for people to use less physical effort. So a great example here is those benches along the path where if you're unable to exert enough strength to go the entire way, there are areas where you can take a break and you can recharge to keep going. Number 7 is proper size and space for use. Really what this means, and it kind of goes back to the dimensions of a shared use path, but really it's you need to make sure that your shared use path is right sized. It needs to be large enough to accommodate all potential users, wheelchairs, recumbent bikes, cargo bikes, basically, any type of user that you're expecting on your path, you should make sure that your path is large enough to accommodate them. And so this image is actually a great example of that, where you've got, what's that, 1, 2, 3, 4, 5 people all using the shared use path. The path is clearly wide enough, everyone is comfortable. That's really the essence of that principle. The second half of our discussion is we want to rethink the sustainability of paths. So a lot of local authorities, they really like shared use paths. They talk a lot about its sustainability benefits, its health benefits, right? They're very affordable in many cases compared to other types of infrastructure. But when you're approaching shared use paths from a view of assuming sustainability, you're ignoring a lot of the real impacts that developing this infrastructure can have, right? So your life cycle cost, there's very little examination of that. There's very little examination of disruptions to local wildlife, the local ecology when you take down trees to build your shared use path. Think about construction emissions. Think about the design of the path. So there's a lot of factors that go into making a path sustainable that many times engineers, planners, policymakers do not take into account when they talk about paths as sustainable. Well, one of the findings was actually from Baylor and Waxmunski. They developed a method called green paths. And what this does is instead of assuming paths are sustainable like previously, they developed the methodology to measure the sustainability of paths. So they used a point system where the design of the path, is it made using sustainable methods, sustainable materials? Is your labor coming from unions? Did you have community input? They've taken a lot of different aspects of sustainability. They count it up, give it a score, and they attach it to the path. And so this is a really great way to move away from, well, we're going to assume the shared use path is sustainable to we can prove that this path is more sustainable than an alternative. And so that brings us to where shared use path research needs to go. Throughout our review, we found that users with disabilities or different abilities were often not discussed in the literature. There's a lot of focus on level of service, there's a lot of focus on capacity, connectivity, but we're really ignoring a large subset of the population who may not be able to take advantage of this piece of infrastructure. And specifically, conflicts between users. We're ignoring a lot of comfort, particularly from wheelchair users, mobility users. A lot of this has been absent from the literature and should probably be investigated moving forward. Thinking beyond level of service, right? So a lot of the previous research, I want to say nearly half of the papers focused on some aspect of level of service, right? We need to start incorporating more than just capacity into these analyses. We need to start thinking about safety, user conflict, accessibility, comfort, non-normative individuals, right? There needs to be a little bit more in level of service beyond just the traditional aspects of capacity. And really what we're building towards is a holistic approach. We need to start looking at shared use paths as part of a larger universally accessible system in our communities, right? We need to be able to interact with shared use paths and cycle lanes and sidewalks. It really needs to be all tied together into something larger. And it's also important to have sustainability in mind when considering all of this. That brings us to our conclusion. Shared use paths are really great. They're very flexible. However, they have a lot of inherent drawbacks. You're dealing with a hybrid infrastructure system where you're supporting both cyclists, pedestrians, you've got some other types of mobility in the mix, right? There's a lot of complexity that may not always be considered when people are designing these. Prior work really focused on that level of service. Not to say that level of service isn't important, but we need to start looking more at the equity and accessibility of our paths to make sure everyone can benefit from these. Universal design, we found that this is a really great idea that can help guide shared use path development, but we also found that for every accessibility feature that is well executed, there are others that are really poorly executed. So we really need to find a way to develop a consistent application of universal design principles on these shared use paths to help improve that accessibility of paths. And lastly, we really need to make sure that sustainability is never assumed when we build these paths. If your goal is to have more sustainable transportation, you need to be able to quantify it. And we're finding that there's very limited tools, but they are emerging on shared use paths to help guide that. And with that, that is my presentation. I'd like to acknowledge our funding partners, the Natural Sciences and Engineering Research Council of Canada, and the City of Edmonton for funding our research, in addition to my co-author, Dr. Stephen Wong. Thank you very much.
Thank you, Edward. I really appreciate your presentation. So we are open to the questions. We have 4 minutes for the questions. Any questions from the audience?
There's one comment. Anything about how often shared use paths are built in ways that support travel for the purpose of getting places and not recreation? That's actually a really great question. And in our review, we actually did not find very much about the difference between we were building this for the purpose of travel versus recreation. A lot of the studies we found were actually, oh, this shared use path is part of a park and having leisure opportunities, whereas the other is been, oh, the city would like to connect two neighborhoods. So it's actually a really great question, and I think it's something that we can look into as we move forward with this research.
Any other question? If not, we will move with the next presenter.
Oh, sorry, we
Kayali.
have a second question. I'm curious about the regulations for shared use paths in Canadian context. Is it similar for most of the cities? This is a great question. In Canada, we have a very decentralized, I suppose, approach to shared use path standards. I think in general, they're very similar in terms of, oh, you need to have a minimum width and you need to make sure that, the grading is all proper and stuff. What I can say is very different across Canadian cities is actually accessibility features. So some jurisdictions are more, I would say they implement it a little better, right? They have tactile or truncated domes at your curb cuts and the center lines, whereas other municipalities don't really focus on that. So it's very inconsistent, but there is a baseline that most cities sort of adhere to. Um, yeah, a really great question. And
Thanks.
there's another one. No question, most multi-use paths are through parks. There's one in Toronto where the park itself links two major streets was used as a cut through. Yeah, that's that I would agree with that. There's a lot of it, like shared use paths are very diverse. Sometimes they're very short. Um, Really, we need to make sure that they're designed well so people know that they exist and they actually take advantage of them. How often were facilities determined to be too small for demand? Well, this is another great question. It's very difficult to quantify this, but any shared use path below about 8 feet wide was found in the literature to have like it was impairing mobility. So you had much higher rates of conflicts, you had much lower capacities. Most studies that we went through really did not suggest going any narrower than 10 feet, right? If you're going to go less wide than 10 feet or 3 meters for us metric individuals, You need to be very careful about where that happens, and it should really be avoided if at all possible, right? If you have a very narrow pathway that is constrained by outside factors, that's one thing, but it is very discouraged. Following up on demand, does it follow build it and they will come? Is that a chicken and egg problem? This is another great question. Now there's no shared use path specific studies that look into this induced demand, right? We know in other parts of transportation, right? Like we know that this is true for roads. There's a lot of evidence that does suggest for bike lanes this is true. No one's investigated that on shared use paths. Um, I would like to assume that if you build it, people will use it. Uh, but there's no specific study on shared use paths about that. Thank you for the
Okay.
question.
So we may have other questions that come up, okay, but let's keep this for now and let's move on to the next presenter. Thank you so much, Edward. The next presenter is Kaya Lee, is a second-year PhD student in transportation engineering at UT Austin. She works on traffic safety and automated enforcement, supervised by Dr. Kara Kokelman. She received her bachelor in water and hydropower engineering with a minor in law from Hawaii University and her master in transportation engineering from UC Berkeley. All right, thank you so much, and the stage is yours.
Can you hear me clearly?
Yes.
Okay, yeah, thank you for the introduction. So hi everyone, my name is Kelly, and today I'm honored to be here to present our work about pedestrian travel distance and crash rates across US settings. So as a start, road safety is actually a global challenge. Every year, about 1.2 million people are killed and more than 50 million people are injured in road crashes. And in 2024, actually, the US is falling behind other countries. 39,000 road deaths happened in the US last year, which is about 1.2 deaths per 100 million vehicle miles traveled, which is 2 times higher than France. And actually, the crashes deliver substantial losses. It costs every American approximately 1,300 in economic costs and 4,100 in comprehensive costs every year. So that's a lot of money here. And for the pedestrian and cyclists, they are called the vulnerable road users because they are more easily injured compared to the drivers. So in 2023, more than 7,000 pedestrians are killed and more than 67,000 are injured in 2023 in the US, which is about 2.37 pedestrian deaths per billion vehicle miles traveled. And for the cyclists, 1,000 of them were killed and more than 46,000 are injured in crashes. Although like the pedestrian crashes per vehicle miles traveled appear stable in the US, but actually the pedestrian and the cyclist deaths are increasing by 68% and 63% respectively in previous 11 years. And we can see like the share of the pedestrian crashes of all crashes deaths are also rising to 18% in the US. And based on this background information, actually, we have 2 research questions here. The first one is where people actually work most. And the second one would be like where like are pedestrians most likely to have an accident. And we actually found one similar research, but this one is conducted like at the county level and only consider the fatalities. So the county level is pretty disaggregate. So we want to be more specific. That's why we try to do this work. And in order to get the working miles traveled per day by county level, we actually use the following data sets. The first one would be 2016 to 2017 National Household Travel Survey data. This data includes about 130,000 households, covers more than 900,000 person trips per year. And in this data set, less than 10% are work trips here. And we also use the American Community Survey data to collect the land use variables, and also like the population density and job density here. The network density and intersection density are included in the EPA smart location data. Yep. And besides these variables, we also include the percentage of the greenlands, which is a percentage of the parks from the National Land Cover database. Oh, oops. So for here, given the high number of non-working trips, so we use a hurdle regression model here to split the working miles traveled into two parts. The first model would be like the probability of the person choose to work on the survey day. And the second part would be if the person decides to take a work, then what's the working distance would be. And for the first part, we use a logistic model here. And we can see from the table that actually the younger female with smaller household size and no vehicle and also higher education and income are more likely to take a walk. And we can see like the vehicle ownership here and the network density are actually the two most influencing variables when people decide to take a walk. Regarding the land use variables, actually people living in regions with dense jobs and also intersections are less likely to work here. And as the second part is the distance model, we used the exponential model to model the working distance if the person chooses to take a walk. And we can see that in contrast to the previous model, actually older males, which has a work and also more educated, are working longer distance on average. And compared to the previous model, actually the land use variable here actually have little effects on working distance, except the network density. And in this model, the age, education level, and also the intersection density affects the working distance the most. So based on the previous model, we actually got the flow chart as in the figure. So after we get that, we can get the vehicle miles traveled per day per person. And after getting that, we try to incorporate the public use microdata area data. So this data actually includes the public use microdata areas, which is geographic units with more than 100,000 population. And this data set actually includes the demographic and also the housing information for each sampled person and also the person weight for each observation. So based on this data and also the WMT per day per person model, we can get the working miles traveled per day per capita at the PUM level. As the PUMS is actually not very commonly used in real life. So we also introduce a PUMS and a county reference to deliver the vehicle miles traveled per day per capita at county level. So after that, we actually got the results as the figure shows. The figure shows the model-based estimates of county-level working miles traveled per day per capita. And in the US, we actually got a total of 126 million working miles happening per day by those who living in the US and also those excluding international visitors. And one point here is that as we only got a sample of the NHTS data, and the QMS data only includes like the people living in this region. So based on that, we only get an assumption here. It's like people will just work in their home county. So we are actually not including working trips like happening outside the home county. And this table shows the top 10 counties by working miles per day per capita. And the average of the working miles traveled in the US is about 0.38 miles per person per day. So for so far, we actually answered the first question, is like where people work most here. And for the second question is where the crashes per working miles traveled are highest. And we got the data from the US fatality analysis reporting system. And more than 8,000 pedestrian and cyclist deaths happening each year. So we try to use the data from 2018 to 2022, which is 5 years of data here. And this figure shows the pedestrian death rates across the US per 10,000 working miles traveled here. And the average pedestrian death rates per 10,000 working miles traveled in the US is about 0.42. And we can see that the Texas, Georgia, Arizona, and California actually has the highest pedestrian death rates. But noticeable here is like here some counties with very high pedestrian death rates are probably due to our assumption about the working trips is only happen in the home county. So some counties with many visitors can have very low working miles traveled, and that may result in a very high pedestrian death here. And this table summarizes the pedestrian and also the cyclist fatalities in the US over the past 5 years. And we can see like the ratio of pedestrian deaths and cyclist deaths is about 8.0, and they most happen on Fridays and Saturdays among males and urban areas. Also for the location of where it happened, actually 75% of deaths are happening at the mid blocks, which is like between the intersections, and 2/3 of them are happening without sidewalk alongside. And for summary, in this work, we actually is a very early age of like we analysis the working miles traveled here and also the pedestrian crash rates. And for here, we also consider the demographic and also the land use variables. And we find like actually the demographic variables affect the work probability and also like the working distance. But actually the land use only have little effects on any given work trip distance. And the older and higher education males are more likely to take a longer work on average. And the Texas, Georgia, Arizona, and California have the highest pedestrian death rates per 10,000 working miles traveled. As this one is just an early age, actually we put our future work into 3 parts. The first one would be we try to also incorporate the crash severity to include all kinds of crashes here, not only the pedestrian deaths. And the second part would be like we also try to use different units to get the pedestrian rates, including like the bike miles traveled and also vehicle miles traveled to estimate the pedestrian deaths. And the third one is like the data we use here is from 2016. So we probably will shift to the 2021 NHTS data. And yeah, I think that's it. And thank you for listening. So please let me know if you have any questions.
Thank you so much, Kaya. You have one note and some appreciation from Edward. So can you read and also Alex?
Oh.
So if you look at the chat and read the question a little bit louder.
Yeah. Yeah, I think the first question is like the working miles is traveled is based on NHTS, but NHTS likely doesn't include all trips around the block. Miles traveled for pedestrian and bike is an interesting question on how to define things like working miles traveled. So the vehicle miles traveled is easier. All those miles are on the road. Yeah, I agree. The first comment, and I think the problem here, like why we try to do this work based on the working miles traveled, yeah, because like for if we want to do the vehicle miles traveled, actually, maybe in some regions that is very like busy streets, but not actually many pedestrian like walk there, then there's some probably issue if we want to get some like countermeasures for designed for pedestrians. That's why we want to focus on the pedestrian, like where they get hit easily. That's why we try to use the walking miles traveled here. But this is also like, yeah, I agree. Like we probably will also incorporate the vehicle miles traveled here to get a better sense. And yeah, I agree, like the working miles traveled will be likely lower, but exposure more because of the block size. Yeah, I think currently our like works possible issue is the working miles travel actually is very hard to get if the person is not working in their home county. So if we want to try to make it like the census tract level, it's very hard to do that because like many people work in a different census tract. But yeah, I think that's a very great question. And is there any other questions?
Any other questions from the audience? Feel free to turn on your microphone and ask directly. If not,
Yeah, I will stop sharing.
yeah, thank you so much. I
Thank
really
you.
appreciate that. Great presentation. So the next speaker will be Parsa Farhani, is a PhD student in civil engineering at University of Colorado, Denver. In this presentation, he shares a modeling framework that combines crowdsourced and ground truth data to forecast bicycle and pedestrian volumes across Michigan. All right, Parsa, feel free to share your presentation.
Thank you, Dr. Mahmoudi. Can you see my slide? First slide?
Yes.
Great. So, hello, everyone. So today I'm going to share my research on capturing panel effect in exposure models using crowdsourced bicycling and pedestrian data. So first, to start with, why did we do this research? Transportation planners always need solid count data to make decisions. Like in our case, to think where they need to build a new bike lane or which sidewalk needs fixing. But as you know, physical counters are expensive and they only sit on a few streets. On the other hand, we have crowdsourced apps data like Strava. They can give us tons of data everywhere, but they're mostly skewed toward recreational users. So our goal was to combine the Strava's data with more reliable counter data in order to predict bicycle and pedestrian volume using a mixed effects random forest approach to fill those gaps. And to do that, we used mixed effects random forest, as I said, and we did that for summer seasons from 2019 to 2022 across 3 clusters in Michigan: Detroit, Ann Arbor, and Kalamazoo. Talking about literature review, so recent studies have used crowdsourced data like Strava, Streetlight, and MuVision to predict bicycle volumes mostly. Strava in particular has shown a good alignment with commuter behavior in many locations in previous study when it was used with other traditional data like manual counts. But these data sets have their own limitations, like coverage gaps, lack of control over pre-processing, and also sample bias. Also, combining this data set with traditional data is not always a very straightforward process. On the modeling side, researchers have tried everything from Poisson to negative binomial models. Recently, they've tried machine learning models like random forests or neural networks. So these newer models often perform better in terms of prediction accuracy, but they don't address the problem of clustered data, where we have multiple measurements that come from the same region. In our study, we used the mixed effects random forest model, or MERF in short, to explicitly handle this spatial and temporal clustering in the data. And this lets us build models that capture both population-wide relationships and site-specific deviation. This is something that traditional machine learning or statistical models miss. And a novel part of this study is that, to our knowledge, this was the first study to explore Strava's walking data for pedestrian volume estimation, because Strava only recently began sharing its walking data, and till now it hasn't been evaluated against ground truth pedestrian counts. And of course, there are concerns like with Strava cycling data that walking data may overrepresent recreational users like runners. But one of our goals here in this research was to address this gap by benchmarking Strava walking data against actual counter-based pedestrian volumes. Before jumping into the methods, I want to give you a quick overview of the study area. So we focused on 3 urban clusters: Detroit, Ann Arbor, and Kalamazoo. So here, this map, you can see the locations of permanent bike and pedestrian counters. For each of these locations, we calculated monthly average daily traffic, and our approach allows us to use the contextual similarities among segments like land use patterns, network connectivity, and weather to predict volumes, even in places where we have no physical counters. And this geographical clustering could both be a strength for our model training and a limitation, which we'll discuss later in our presentation. And for this study, we combined 3 main data sources. We used permanent bike and pedestrian counters from 2019 to 2022, and we summarized that into monthly average daily traffic. We also used the crowdsourced Strava data for the same months and extracted monthly average daily traffic at the street segment. And also we gathered a set of more than 160 contextual variables, things like land use measures, including park area and retail density, network features like intersection density, and weather data such as precipitation, temperature, and humidity. And to further make sure our data was reliable, we cleaned the data. We cleaned the counter data. We removed days with 0 counts. We adjusted for daylight saving time gaps, and we filtered out any extreme weather anomalies. And for each side, we matched the count data with the corresponding Strava counts. And finally, before running our MERF, we did some feature selection. We dropped variables that had low variability or the features that were highly correlated. That left us with around 40 feature inputs for our model. In this slide, you can see the comparison between the monthly average daily traffic from Strava on the right and the data from counter volumes. And in general, Strava tends to report lower values across all sites compared to the counters. And this is the data for pedestrian counters and the comparison with the monthly average daily traffic from Strava for the same locations. So now let's talk a little bit more about cluster data. meaning where we have measurements that are repeatedly for each subject or location. So when dealing with this type of data, we have four main strategies that we can follow. We can first build a separate model for each cluster, but it doesn't scale well because each model will have little or no data, so it can generalize. We can also train a single global model across all the clusters. This helps capture population level patterns, but it misses cluster specific patterns. Another approach could be including cluster ID as a feature, but this could become computationally challenging in the models, especially if we have too many clusters. A very good solution to this could be using mixed effect models that account for both global trends and cluster level variations. So as I said, mixed effects models do a great job handling the clustering structure that I mentioned, but they're not well suited for modeling nonlinearities. On the other hand, we have traditional random forests that are great for capturing nonlinear complex relationships, but they don't account for clustering. So combining them, mixed effects random forest, or MERF, developed by HGM in 2014, gives us the best of both methods. It fits a random forest to capture the global fixed effects and then uses an EM algorithm to estimate random intercepts for each of the sites. So in our analysis, we use the MERF package in Python. We manually tune two hyperparameters, the number of EM iterations and the number of trees in the forest. We also did an 80-20 split at the site level to make sure the model is tested on unseen locations. And we used the 5-fold cross-validation to reduce overfitting. And this whole setup allows the model to capture both general patterns and the specific site-specific differences that might otherwise be overlooked. Here we have the results for the bicycle volume prediction model. On the training set, MERF achieved an R-squared of 0.98, RMSE of 16.49. On the test set, R-squared was 0.79, RMSE was 64.87. Mean absolute error was 11.64 in training, 48.25 in testing, corresponding to MAPEs of 8% and 31% respectively. And the numbers show strong in-sample fit and reasonable generalization, given that we only had a few counters informing thousands of segments. And on the right, we have the sharp summary plot that shows how different input features influence the model's prediction. Each dot here represents a prediction for a specific observation, and its position along the x-axis shows whether that feature pushed the prediction higher or lower. So looking at the Strava here, we can see that higher Strava counts shown in pink are associated with higher predicted volumes, and lower Strava counts shown in dark blue tend to pull predictions down. So it shows that the model is learning if a Strava activity and data is available. It could be a good indicator of actual volume. We also have grass area that showed the same pattern. As we'd expect, more green space encourage more biking. And we also saw that features like temperature contributed positively, showing that people are more active when weather is nice. Also, slope and precipitation both tended to reduce the predicted volumes, as steeper areas likely see less biking, and higher precipitation levels are linked to lower biking activities. And here we see the mean absolute champ values by feature and location, which basically tells us how much each feature contributes to the model's prediction on average in each location. Higher values mean that feature plays a bigger role in explaining variation in bike volumes. Taking a closer look at the results here, we can see that grass area really stands out in Detroit and Flint, but it's less important in Novi, Michigan. That could make sense because green space in more urban dense areas probably encourage more biking. Slope, as you can see, has a clear difference in Novi compared to Detroit. Novi, as you know, as a suburban location, This could be a reflective of the importance of slope in more suburban areas, showing that even small hills might be a deterrent factor and discourage people from biking. The Strava MADT showed to be important in Detroit and also mattered in Ann Arbor and Flint, but not so important in Novi. That could suggest that crowdsourced data like Strava works best in more active areas where people are more likely to use tracking apps like Strava, but it doesn't capture activity very well in quieter areas. So what was powerful here is that MERF doesn't just learn one global patterns, and it learns how the importance of features shifts across cities. Here for our pedestrian model, you can see that R squared was again for training was 0.98, RMSE was 35.91, and the test set R squared dropped to 0.72, and we had an RMSE of 145.2. And the bigger errors that we have here compared to the bicycle model could be reflective of Strava's undercount for everyday walking data, since Strava data tends to lean toward recreational or fitness focused walkers mostly. And on the right, again, we have the sharp summary plot. You can see that same as in bicycle model, higher counts of Strava MADT lead to the model predict increased pedestrian volumes. We have also the retail area. You can see the model picks up on that, and higher values in retail area is associated with higher pedestrian volumes. Slope shows the same pattern as what we saw in bike model. Steeper areas tend to discourage walking. And also we have two bike-related features. It's likely that if a street is well designed for cyclists, it also could be a good environment for walking. And here in the mean absolute shaft, showing mean absolute shaft values by feature and city for pedestrians, we can see that Strava again, same as in bike model, is more significant in urban areas like Detroit and less in suburban areas. Bike usage density, as you can see, really stands out in Novi, but less important in Detroit. Novi is more of a suburban, so bike trips are likely to concentrate along the main few corridors. So when we have high bike counts in a corridor, it's very likely that the same corridors carry most of their areas for traffic. In Detroit, that's mostly a dense urban network. Bike trips mostly scatter across many streets, so it might not be a reliable signal of overall street activity. We also have a slope that you can see show a very similar pattern to our bike models. Also here we have retail that show to be more important in Detroit comparing to Novi, and likely shows that more urban places like Detroit's busy commercial strips with lots of shops can encourage more walking, but in quieter places, adding stores might not automatically turn the segment into a busy walking zone. So in terms of practical implications, we can use our predicted volume maps to rank corridors, and it can help us decide where infrastructure upgrades are needed most. We also can layer crash location data on top of these volume heat maps, and we can get a clearer picture of actual safety risks. This can let us focus safety improvements where they matter most. And finally, we can combine the forecasted increases in pedestrian and bike volumes with cost estimates to create a simple return on investment metric, basically dollars spent per additional user. And this approach makes it way easier to set transparent and defensible priorities for funding. And in terms of limitations, before developing the model, we compared the ground truth with streetlight and Strava data. Based on this analysis for two sites that you can see here on this table, the crowdsourced data from Strava showed to be much lower than counter location data, which was expected, as the crowdsourced data does not capture all the trips. And that's the reason they need to be supplemented by more reliable counter data. And as you can see, streetlight seemed to be more reliable as it was closer to counter data. But the problem with Streetlight was that it stopped providing non-motorized volume data at road segment from 2022. So Strava was the only crowdsourced data that was available to us. Other limitations, we can mention that counter data that we relied on was spatially clustered in urban areas that can limit how well our model can generalize to rural areas. Also, most of the data from Strava comes from people using it for workouts like fitness rides or runs. So it tends to miss more casual users like older adults or people walking to work. And this bias might affect the representativeness of Strava data. Finally, because the data we collected were during May to September, it may miss some of the more detailed seasonal or behavioral patterns. And finally, to wrap this up, our mixed effect random forest model successfully combined crowdsourced and ground truth data and provided accurate prediction of bike and pedestrian volumes. We saw strong performance in Michigan's main urban clusters. So this research can provide practical tools to prioritize infrastructure improvements, enhance safety, and support smarter funding decisions. Looking ahead in the future, we can incorporate additional data sources like video and mobile phone data, and also apply this approach in other states like in Colorado, where we are, to explore whether different results show up. Thank you everyone for your attention. I'm happy to take questions. If not, my email address is here. Feel free to reach out. Thank you.
Thank you, Parsa. So we are open to questions. We have 4 minutes. Any question from the audience? Okay, thank you so much, Parsa. We are going to move to the next presenter. Baldev Giri is a PhD student pursuing his degree in transportation engineering at the Zero Lab at University of Arkansas under the supervision of Dr. Suman Mitra. His research interests include travel demand modeling, travel behavior, emerging modes of transportation, and equity in transportation. So, Baldev, please start sharing your screen. Then we see your screen now. And yes.
Can you hear me?
Yes.
All right. Okay. Thank you for the introduction. Good afternoon, everyone. I'm Baldev Giri, a PhD student at the University of Arkansas. The name of my advisor is Dr. Suman Mitra. I work in the Zero Lab. And the topic of my presentation today is analyzing unmet travel needs in the USA, generalized structural equation modeling approach. Nearly 1 in 4 Americans take fewer trips than they planned or than they need each month. This is a data which came from NSDS 2022, which is National Household Travel Survey data. And this research is based on this fact and based on the travel survey data. Here is the structure of my presentation. I will briefly explain each section of my paper from introduction to conclusions. Let's go into the introduction. So what is unmet travel needs? Unmet travel needs refer to the phenomena where intended trips are not fulfilled because of various reasons. The reasons might be related to transportation or non-transportation, such as health reasons. And studying unmet travel needs is important because unmet travel needs is related to reduced mobility, and unrealized mobility or reduced mobility, it directly undermines employment, education, and overall quality of life. So the objective of the study is to explore the reasons and determinants of people's unmet travel needs in the USA using 2022 National Household Travel Survey dataset. Let's talk about what the previous literature has done on this topic, what do we already know, and where are the gaps. So there are some foundational policies which aim to improve equity and improve the mobility of people. There are landmark policies such as 1964 Civil Rights Act, Intermodal Surface Transportation Equity Act, Transportation Equity Act of 21st century, and other policies. But there is not a single federal policy labeled as addressing unmet travel needs. And policies, they often overlook the mobility needs of disadvantaged populations. In previous studies, researchers have used various different terms to address this same phenomena of unmet travel needs. For example, suppressed travel, unrealized travel, some term it as latent demand, or forgotten travel. And in terms of methodological approach, studies have applied enhanced travel diaries to study suppressed travel by knowing the assessing and rescheduling of travel. And most studies have focused on older adults, and they focus in small areas. And some studies, they have identified barriers and they have provided theoretical framework, but they lack empirical evidence, empirical calculation for unmet travel needs. So here are some gaps from previous literature that this study aims to address. This study focuses on general overall populations, applied statistical modeling to find out the most affected demographics. It attempts to address the indigeneity issue, to find out and to calculate the indirect relationship which might influence the likelihood of taking fewer trips, and provides national level insight. Further, this study has explored the reasons behind unmet travel need in depth. Let's explore the data we have used briefly. The study uses, like I said before, 2022 NSTS data. The 2022 version captured around 8,000 households and 17,000 individuals using address-based stratified random sampling. Although this is smaller than previous NSTS versions, the data set maintains robust analytical power due to the improved sampling method applied. So let's look into how we have analyzed the data. For the analysis, for the methodology, first we classified respondents into 4 different groups. First is people who did not mention taking fewer trips at all. Second group, people who took fewer trips overall. Third group, who took fewer trips due to transportation-related reasons. I'll show you what are these different reasons. And fourth, people who took fewer trips due to non-transportation-related reasons. Then we conducted descriptive statistics and applied generalized structural equation modeling, which helped us examine both direct and indirect influences of various variables on the tendency to take fewer trips. Here's the conceptual model. As you can see in the figure, there are socioeconomic and demographic characteristics which influence people's fewer trips, but these also influence household vehicle count and urban-rural residents. You can see in the flow chart, the arrows depict both the direct and mediated pathways. So structural equation modeling, this captures the direct effect of socioeconomic demographics variables to fewer trips, and also indirectly via the household vehicle count and urban-rural residents, which is residential self-selection. So I ran 3 different models here. Model 1 contrasted anyone with unmet travel needs against those without unmet travel needs. Model 2 focused on transportation-related cases. And Model 3 it targeted non-transportation related reasons of taking fewer trips. So let's dive into the results now. Here, as you can see in the pie chart, around, like I said in the beginning, roughly 24% of adults report taking fewer trips in the last 30 days, according to NSTS 2022. And we have explored this part in depth in further results. Here are the reasons cited for people's unmet travel needs. As you can see, different reasons. There are transportation-related reasons such as affordability concern, transportation not being reliable, transportation not being available to go where they needed to go, transportation not being safe and clean. These are into transportation-related categories, while health reasons, and concerns related to COVID-19. These were non-transportation related reasons. Here are the results from basic descriptive statistics. I have highlighted the main results here. The results show that females, Black or African American, older adults, and people from lower income households, they are overrepresented among those who took fewer trips. And further, we dug deeper into just these transportation related reasons to see what demographic variables, what group of demographic population choose which kind of transportation related reason for their fewer trips. So as you can see here, like I have highlighted the major reasons. The results show that females are overrepresented across all transportation barriers. Non-drivers, they report mainly safety, cleanliness, and coverage related issues, probably because non-drivers use public transit. Black or African American mainly report the reason of reliability, which might also be related to use of public transit more often, while other races report concerns related to cleanliness and safety. You can see other results, but surprisingly, even unemployed individuals, they report taking fewer trips because of affordability concern, maybe because they need to travel more often. Here are the travel characteristics graph, and one major thing to notice here is that people who took fewer trips due to transportation-related reasons are underrepresented across all the mobility measures, from trip frequency, average trips per day, average person miles traveled, and average vehicle miles traveled, which proves the point that those people who mentioned taking fewer trips due to transportation-related reasons, they are actually transportation disadvantaged populations. So here are the key results from a GSEM model, Generalized Structural Equation model. As it was not possible to present all the results, I have highlighted major results here. Most of the results are similar to the results from descriptive statistics explained earlier. At the person level, females are more likely to reduce trips overall, especially for non-transportation related reasons. Older adults were also found to be more likely to reduce their trips, often tied to health challenges. For unemployed individuals, they were also found to report higher unmet travel needs. Similarly, Black individuals are more likely to reduce trips mainly for transportation-related reasons, which points to systemic barriers in mobility access. And interestingly, drivers are more likely to reduce trips for non-transportation-related challenges, non-transportation-related reasons, with challenge the common assumption that driving ensures greater mobility. Turning to household and location factors, lower and middle income households are more likely to experience unmet travel needs, both for transportation and non-transportation related reasons. we can see the similar results for households with children. But having more vehicles in a household reduces the likelihood of unmet travel needs, which is pretty intuitive. And surprisingly, we found no significant difference in unmet travel needs between rural and urban areas, indicating that mobility challenges are there, but they are not significant in those regions, even in census regions. These are the results from our generalized structural equation model. And here are some policy implications. These are like recommended policies based on like previous literature and based on the results of our study, improving affordability and access to transit, expanding family-oriented transit services for households with children, enhancing mobility for seniors and individuals with health needs, are the most intuitive actions that can be taken to address unmet travel needs, because these are the groups which are found to be more significant in terms of taking fewer trips than they planned. And further, enhancing transit safety and security is warranted, as these are also major reasons for people taking fewer trips. So overall, like I explained the results of the modeling, the study provides comprehensive analysis of socioeconomic and demographic factors which influence the likelihood of taking fewer trips. To summarize, the results from descriptive statistics and modeling show that these all the groups, they take fewer trips than they planned in the last 30 days, and they are significant. But the model also show the difference between transportation related fewer trips and non-transportation related fewer trips. And here are some findings which are in contrast to findings from previous studies. Non-drivers, individuals with lower educational levels, and those living in rural areas. These variables did not appear significant, which is in contrast to findings from previous studies. So this study is, however, not without limitation. First, we rely on self-reported travel survey data, so there might be recall bias. This study does not consider trips that were never planned due to a lack of transportation infrastructure, and there is no possibility of capturing that. And since NSTS does not collect the type of trips that were like foregone, so we are not able to analyze that aspect. And future studies could consider like more residential self-selection variables or more location variables to find out which areas are facing more unmet travel needs in the future. Thank you for your time and attention. Any questions or comments will be really appreciated.
Thank you. I appreciate that. We are going to wait for the questions now. Alex, I appreciate your presentation.
Thank you.
Yeah, I just put a comment in the chat on my question.
Oh, okay.
It would have been useful to see disability status variable. Yes, we were like considering this variable, but because like there is already the reason, like health related reasons, so we thought that this health related reason would capture the disability status as well. So we consider that. Yeah, but yeah, we can incorporate and see how that affects the modeling results. Thank you for your comment.
Yeah, like my question was like, we know NSTS collect the information whether a person is disabled or not.
Yes.
So if a person is disabled, he or she might like respond yes, making fewer trips. So you had like lots of demographic variables that could explain like why they're making fewer trips. So that's a suggestion. And like the second question was like how like in your conceptual model, you are showing like, yes, social demographic variables is impacting the urban-rural status. I was not clear on that. So could you please comment on that?
Oh, that is a residential self-selection, like people choose where to stay, in which location to stay, based on their like travel preferences in the future, and which will like ultimately dictate whether they would take fewer trips or not. For example, a person might choose to live in city areas or large cities because there are more public transit and they do not need to use car. That's like residential self-selection we try to incorporate in the study.
So the structural equation model had this effect, like how the social
that is not so significant actually. In the descriptive statistics, we found that urban residents are more likely to take fewer trips because maybe they have more travel demand than the rural residents, and rural residents may not even like plan the trips at the first place. But we incorporated that in the generalized structural equation model.
Okay.
Yeah.
Thank
That's
you.
a great question. Thank you.
Any other question? If not, thank you so much all presenters for participating in this session. Thank you both as well. I really appreciate everyone, and I hope you enjoy the rest of your day. Have a good one.
Thank you, Monia, for moderating the session.
Sure, of course. Have a good one. Thank you
You too.
for taking care of this session.
Yeah, sure.
Bye-bye.